Today we're going to be starting part 1 of the acid-base notes. These notes are connected to section 13.1 through 13.25 in your online textbook. So we're going to start off talking about the Arrhenius definition of an acid. Swedish chemist Svante Arrhenius was the first to explain the behavior of acids and bases. Because of their ability to conduct a current, he knew that both acids and bases contained ions in solution. An Arrhenius acid is a molecular compound that ionizes to form H+ in an aqueous solution. So typically we would only think of ionization as occurring with ionic compounds. So we know that something like sodium chloride, NaCl, it breaks up into Na+1 and Cl-1. So for an acid, even though hydrogen is a nonmetal, it can actually go through this process as well if it is in a highly polar covalent bond. So for example, when you have something like hydrochloric acid, you have HCl, the hydrogen can break apart from the chlorine to form a +1 charge, and then here you can see that that +1 charge is attaching to the water. That makes something else called hydronium. So hydronium is where you have H3O+. Acid solutions are containing electrolytes, which means that they conduct an electrical current. They also have a sour taste. So lemons, vinegar, oranges, sour candies, they all have a type of acid inside of them which adds to the taste. Acids can also change the color of certain types of indicators. So a common one would be something like litmus. So here you can see litmus paper being put into an acid and it changes color. You could also have phenolphthalein, so this is used within titrations. So in the presence of an acid, you would have a clear solution, but when it becomes more basic, then it becomes this pinkish purple color. We'll talk more about titrations later on. Acids react with active metals in order to produce a hydrogen gas. So you've actually seen this before when we had our single replacement unit. So remember the activity or reactivity series down here. Elements that were above the hydrogen were more reactive than hydrogen and able to react with it. Acids also react with bases to produce a salt and water. When I say salt here, it doesn't have to be sodium chloride. It could be any kind of ionic compound. So it could be calcium chloride or anything else. So they make that with water, and this is known as a neutralization reaction. So the acid and base cancel each other out, and you end up with a neutral pH of 7. So within our naming unit, we kind of skipped over all of the acid naming because at the time it was much earlier in the year, and I was afraid that you wouldn't remember it by the time we actually got to acids and bases. So we're going to learn how to name acids now. If you have an ending that ends in IDE, you change that ending to IC. So ide to ic, and you also add the prefix hydro. This is used whenever you have a hydrogen bonding to a regular element, like the chlorine example here, or maybe bromine, or fluorine. So this is hydrochloric acid, this would be hydrobromic, and hydrofluoric. In the Tyler DeWitt video that you're going to watch for homework, there's also a mnemonic that he uses for this. And the mnemonic is, my ride has hydraulics. So IDE to IC, and you also have the hydro prefix. All right, the rest of our rules are going to deal with if we have polyatomic ions. So for this one, if you have an ATE ending, that changes to IC. So here, NO3 with a -1 charge, if you look that up, that is nitrate. So the ATE changes to an IC ending, it becomes nitric, and there's no prefix here, there's no hydro. So that helps to differentiate between when you have the polyatomic and when you have it bonded to a regular element here. There was also a mnemonic for this one, which was, I ate something icky. So we have ATE going to IC. Our next rule deals with polyatomic ions which have an ITE ending. So nitrate is NO3, nitrite is NO2. When you have an ITE ending, you change the ending to OUS. So this would become nitrous acid. The mnemonic for this one was Sprite is delicious. So ITE to OUS ending. Now those are the main three that we're going to use most of the time, but you could also run into situations where you have an extra oxygen compared to the ATE ending, or one less oxygen compared to the ITE ending. So we know that NO3 was nitrate. So what would we do if we ran into something which was NO4? The prefix of per here shows us that we have an extra oxygen compared to this. So NO4. Over here, we also know that NO2 was our nitrite, but what if we have one less than that? What if we have NO? The prefix of hypo means that we have one less than that situation. So hypo and then nitrous acid. Now, there's something that you can write out that might help you to keep all this stuff straight. So we have per and then 8 to ic. 8 to ic. ITE to OUS. And then hypo. ITE to OUS. All right, so on your common polyatomic ion sheet, you might not have all of the members of the polyatomic ion family. But if you know one of them, then you can scale up or scale down to anything else that you need. So I'll show you an example of that with sulfate, SO4. Sulfate is on your polyatomic ion sheet. So SO4 goes with the ATE right here. If I have one less oxygen from that, I just go down this list. So that means SO3 would be called sulfite. If I go down again, that means that SO2 would be hyposulfite. If I go up from sulfate and make this SO5, then that would be persulfate. And from there you can get all of your acid names. So this would be persulfuric acid, sulfuric acid, sulfurous acid, and hyposulfurous acid. All right, now with the -2 charges here, if you're going in the other direction and you have to write the formula from the name, okay, let's say that I had the sulfuric acid, sorry. I know ic goes back to 8, so I know I'm looking at sulfate, which is SO4 -2. I also know it's an acid, so there has to be hydrogen out in front. All of these acids have hydrogen. Hydrogen only has one electron to lose, so it has to be a +1. This is just like ionic formula writing. I cross my charges down, and I have H2SO4. So that would be my formula for sulfuric acid. All right, moving on, you have to know the difference between monoprotic and the various polyprotic acids. So you know that mono means one. So these are acids that contain one ionizable hydrogen. So one hydrogen could potentially come off of it. Poly means many. So this is one that has more than one hydrogen that could come off. From there you have di and tri, which of course is 2 or 3. So something like H2SO4, this would be considered a diprotic acid, and H3PO4 would be a triprotic acid. All right, so we talked about acids. Now we're going to talk about the Arrhenius definition for a base. So if acids are giving off H+, bases are giving off OH-, which is hydroxide. Now luckily, the naming system for this is not any different from what you've already learned. So since OH is hydroxide, you just put the metal name out in front, and then you have hydroxide. So for example, if I have NaOH, that would be sodium hydroxide. An alkaline solution is another name for a solution that is basic. So all of the alkali metals react readily to produce water, to produce a metal hydroxide and hydrogen gas. So you can see that occurring here. Properties of bases. Bases also form electrolytes. So when you dissolve them in water, they're going to conduct an electrical current. If you remember from our bonding properties lab, we had those little 9-volt batteries with the lights. When you dip that into a solution which has salt in it, something ionic, the light will go off. The same is true for acids and bases. Bases often have a bitter taste and are found in foods less frequently. And soap is a good example of a base. So they would have a bitter taste, very slippery. Bases also change the color of indicators. So litmus turns blue in the presence of a base, while phenolphthalein, the stuff down here, it's going to turn a pinkish purple color. Bases also react with acids to produce salt and water. So this is the same point from the acid slide. Just know that an acid plus a base is going to neutralize. They cancel out. So at this point in class, we would go through our checkpoint. So sour taste, that is an acidic property. pH of more than 7, so that'd be like 8, 9, 10, that would be basic. Proton is another word for hydrogen plus 1, so that would be an acid. Acids give off that. Slippery and bitter taste would be basic properties. All right, for naming here, we have a fluorine which is by itself, which means that we're going to have hydro out in front, so not a polyatomic. Fluorine would be fluoride in a compound, and IDE changes to IC. And then you add the word acid. So hydrofluoric acid. H2CO3, this is carbon 8. I ate something icky, so 8 goes to IC. This would be carbonic acid. And there's no prefix here. Prefixes of hydro are only for the regular element. OH is a base, so this is just named normally. I have sodium and then hydroxide. All right, for the examples on the bottom, we're going the opposite direction. We have OUS. Sprite is delicious, so that goes back to ITE, so nitrite. And nitrite is NO2 with a -1 charge. Hydrogen goes out in front since it is an acid and is a +1 and a -1 charge. 2 charges cancel out here, so I don't have any other subscripts. Hydrobromic acid. The fact that there is a hydro here means that this is bonded to a regular bromine, not bromate or any other polyatomic ion. So you have H plus 1, Br minus 1, they cancel out. Finally, we have calcium and hydroxide. And you need to be careful here because you have to remember to cross your charges. Calcium is a +2 charge, hydroxide is a -1. When I crisscross them down, I need parentheses to show that I have 2 of the entire hydroxide anion. The charges you would erase or cross out. So Ca, OH in parentheses 2 is your final answer for that one. All right, so now we're going to move into the Bronsted-Lowry definition. So there's a few different definitions for acids and bases. An Arrhenius acid gives off a H plus or a proton, so that's basically the same here. Bronsted-Lowry acid gives off hydrogen. The main difference is for bases. The Arrhenius definition, you give off hydroxide, whereas in the Bronsted-Lowry definition, it accepts a hydrogen. So the reason why this is important is because things that would not be considered a base otherwise, something like NH3, could now potentially be included here in the definition. NH3 does have basic properties. It's very slippery. It would have a bitter taste. So it does fall under what a base would look like. So this allows us to include that. A hydrogen ion is commonly referred to as a proton, so I mentioned that before. So acids and bases are either giving up or accepting protons within this definition. All substances that are characterized as acids bases under the Arrhenius are still acid bases under Bronsted-Lowry. The only difference is that this includes more things. All right, conjugate acids and bases. So with this Bronsted-Lowry definition, we have protons being accepted or donated. So here I have water. I'm going from H2O to OH. Within that process, I have given up a hydrogen. I've given it to the NH3. So that makes this an acid. The NH3 took on a hydrogen as it went from NH3 to NH4. So that makes it a base. The conjugate part you can think of as kind of what would happen if you ran it backwards. So if I was going from the right back to the left, which of these two would give off a hydrogen? They both have hydrogen, but in order to go from NH4 back to NH3, I would have to give off a hydrogen. So that makes this like an acid, so conjugate acid. Hydroxide would gain a hydrogen as it goes back to water. So since it's gaining a hydrogen is an acceptor, that would make it a conjugate base. So you should be prepared. If I give you a chemical reaction like this, you should be able to label each item as an acid, a base, or a conjugate acid or base. All right, we're going to finish up the first half here talking about hydrogen concentration. So this is something that you should be able to calculate. If you have your Kw value, this is a constant for the dissociation of water. At any given point in time, in pure water, H plus and OH minus are both 1 times 10 to the negative 7th molarity, so that's their concentration. So when you multiply these two together, you get your constant of 1.0 times 10 to the negative 14th. Now based on that, you can scale up your hydrogen or your base in either direction. You can scale it up or down and then find the concentration of an unknown. If you are simply looking at the concentration and you want to know if something is acidic or basic, if your H plus is greater than times 10 to the negative 7th power, meaning exponents of negative 6, negative 5, negative 4, and so on, then you can consider that solution acidic. If it has an H plus and an acid concentration of less than to the negative 7th, so negative 8, negative 9, negative 10, and so on, then that would be considered basic. All right, so here we're going to try to calculate the concentration of OH minus if we have our H plus concentration. So our equation is that Kw, which is 1.0 times 10 to the negative 14th, is equal to our concentration of H plus times our concentration of OH minus. And in these problems, you will always be given one of the two. So here I'm given my H plus. I divide H plus to the other side in order to isolate the variable that I'm looking for. So I've just solved for OH minus. So now you just have to substitute this number in for H plus. So I have 1.0 times 10 to the negative 14th, and you should always have that number on the top. You're dividing by 1.0 times 10 to the negative 5th. And when you divide those two, you get 1.0 times 10 to the negative 9th power. So that is my concentration of OH minus. Now, if you're plugging these into one of our scientific calculators, make sure that you're putting parentheses around your entire number in scientific notation. Otherwise, you'll end up with the wrong answer. All right, finally, I have some classification practice. So if I have an H plus concentration, which here I have negative 10th power, so this is low. If I have a low amount of acid, that means that this is basic. Here I have a large exponent, relatively large compared to negative 7, of my acid component. So that is acidic. For the next part, if I wanted to, I could convert this back to H+, but I really don't need to. I could do it based on what was on the previous slide, or I can just see that here I have a large amount of base. So that makes it basic. So if you can do it that way in your head, you can save yourself a little bit of work and some time. For our last one, we have 1.0 times 10 to the negative 7th power. This would be exactly neutral. It is right in the center. All right, so this concludes part 1 of our acid-base video. Within part 2, we will start off by talking about the calculations for pH and pOH. We'll talk about indicators, and we will finish up with titration problems.